Okay, so let's begin. So before in my lecture, I'll do a quick summary. So after week 14, so we still have 4 weeks off, and you're supposed to be working on your final exam, either final exam or your term paper. That's lots of time. Of course, I'm open to questions, so you can send me an email or it's office hours. Probably not a really good time for scheduling office hour, but and those you're me, you have to run lots of risk in terms of the exposure to COVID. But anyway, that's good. I'm open to partial questions, so that should help you fulfill your term paper requirement. But also, are you interested in learning other topic related to this course, or is it more than enough? So we'll just close it off with the last topic of this course, which will be text mining, talking about the joint distribution related to inertial allocation. After that, we pretty much finish out all the lecture part of this course. Or you want to hear additional topic, you can probably schedule one additional topic, or just like class ask you, people say, that's enough, that's more than enough to cover in a single semester. Any thought or input on this?
Like which topic, for example?
The one that I have on the back of my mind would be network analysis. Well, I'm not sure if I probably be able to cover that in the just 2-hour lecture, but a huge topic. And for others, it'd be like another application of text mining. We have 2 weeks of text mining related to lecture that should be done. What else? Probably won't jump into the deep learning field. That's way more extensive. It's not entirely related to this course. Or just close it off with the text mining, and after that, you just send me your return paper question for this exclusively on your return paper. Or I can do a quick review of this semester. I think that for a review course, I would just send you a slide, and you can actually learn it yourself instead of having me standing here talking about this. We cover essentially the same material. All right, so I would like to think about this, and you can send me email and see whether you prefer the best. Okay, so let's kick it off. So for today's topic, talking about other technique. Or it's actually more about fixing. I think just like the object that I've been pursuing throughout this semester about fixing standard error. Because in terms of model prediction, or if you're trying to explain something that's already happened, whether the analytical task that you want to achieve is to predict something that you haven't seen before, or something hadn't happened, or to explain to the extent possible something that you already observed or that had already happened. The most important thing is to minimize the part of the error that hasn't been explained by the model, or you fail to predict by the model that fit on the data, right? So throughout this semester, our task is simply to minimize this error, this amount of error. Okay. So here we provide, so today's lecture cover several techniques to fix those standard error. So begin with reciprocity. So begin with the rationale for reciprocal. Then we begin with big one now cross-validation, and it's close relative. Default cross-validation, and then we close talking about bootstrapping, since you probably heard we talked about this. So here's our thread. By the way, there's two of you have set up maybe around like week 2 or week 3 when I first talked about this. That's a little bit too quick. So here, so if I could provide a menu, but it's just a short note. I actually uploaded it on our shared downloads folder, and I'm probably not sure if download folder until you could. So you can read through the derivation process about how each of these tools are doing. But simply, just quickly jumping through. Just suppose y is the real data, real actual data that we have that we collected. So for all the linear regression non-parametric model that you fit on the data, you see the variable in the data set that you try to explain the outcome variable, right? Your primary goal is just to minimize this, so that given the variable that you have, and also the number of observations, right? Then try to fit your model on in order to get predicted value. Your task is to minimize this part, which becomes irreducible error, because no matter what you do, there still exists this amount of random error, right? So you might get a slightly larger error for your prediction, in your prediction for some observation, a smaller error for your prediction for some other observation in this. Okay. So let's suppose in a real world, in an ideal, right, y, the outcome variable, can be entirely captured by some function. I'm not saying that this necessarily means linear regression model or some non-parametric model. It can be any function. So let's suppose y, the variation in y, can be captured by some function as a function of x. Okay. But without it being perfect, so there's definitely still be some amount of variation, okay, such that when you get a predicted value plus some random value, okay, then we can substitute this value into y, right? So that the expected error would just be y minus which is this, right? And we can use some really basic, like square expansion to expand this out. But before that, we need to add one additional term. We just add one extra predicted value. Okay. Then we expand this out. So this part as well, and this part is the irreducible error that we'll confirm. Then now we have this. There's two major components, bias and variance. So what is bias? So bias is actually the part of the error that we seek to minimize for the outcome variable that we're trying to predict. Third, model specification. So here I have one good thing. Model specification. That involves the variable that we're putting here that we try to approximate the variation in outcome variable, right? So that's x. Also, the function. Because you can specify how x is related to y, or vice versa, how y is related to x. So if you remember those exercises that we have done, in, for example, like polynomial regression or other type of regression, because we actually, the other thing we noticed that, okay, x and y, they are partly related, but how are they related? Right? So maybe the relationship between x and y is quadratic polynomial or something follow some degree distribution. We do not know. So the choice of path is very important. So this is the effort of primitive that we try to minimize through one specification by putting the variable as well as the function, the choice of function to minimize this. And here's the variance. So variance itself is not actually the variance of the model variance. It's a mean squared deviation. I have to put a V here. Mean squared deviation of your expected value. No, your predicted value of what? The predicted value here. Around is expected value, which is just its mean. So it's just the variance of the predicted value of y itself, right? Not the variance of y itself. 0 to probably have plus some irreducible error. There's some randomness. So crucially, you should probably see that. So the choice of the function is definitely very important, but also the part of the observation that we use to draw our inference on, because we're going to try to, I mean, like in just a couple months, we have an election cycle going on. And you see that that's the TV channel or political party, they were trying to gauge public opinion through survey, right? But it's not possible that they will interview each and every one of these. Say, will you vote for, which party would you prefer the best? They're only simply that sample some population, but some people from the population, usually around like for Taiwan's population size, usually around like 1,200, or maybe slightly over 1,000. I think they're where we now, and simply, and then we'll check out the distribution of data and say, oh, okay, so our results suggest indicate that this and that percentage of people support this party over that party, and our inference is built down, say, 97.5 confidence interval. Right? But however, in another survey, by another survey house, we actually found out quite different result. Now, of course, that depends on their sampling technique. And also, the population is wrong. So the sampling technique is just, let's say, it's technical issues, and so that actually improve all the time, or depending on what the statistician they hire and what's their favorite statistical method. So I do not want to jump into that debate. But the choice, say, the choice of the population that they actually sample is very important, because we're going to simply do sampling, say, the Da'an district of Taipei City over maybe some district in southern part of Taiwan. You will actually get quite different result, right? The outcome is very contingent upon the distribution of data, and also what's the attribute of the sample being included in the data. And that's very important, especially when we try to do machine learning, which simply we select some part of data, for example, here a trend test foot, and then we fit a regression model on the training data, and use the trend model, or something say that's a piece of insight, right? If you represent the intelligence. The insight we draw from the subdata to test on the rest of the data, which we use as a casting data, casting set. But if for each random draw, we draw a different symbol, or say the composition of of our randomly selected sample are very different each time, then we should get very different prediction result. Because so far we have assumed that, like, so if our sampling method, sampling process is entirely random, then the sample that we get from the population should follow identical distribution, nearly identical. I don't want to say identical, nearly identical distribution. That should be very close to the true population, because we always know they follow normal distribution. So whenever we draw, or each day when we draw, we simply follow. We do say we do a random sampling. I mean, it means that we draw, say, this amount of data, same amount of data all over the sample space. And then the composition of the sample that we draw from the population should be the same. But oftentimes they are not. Because the old view from the very somehow unrealistic assumption that so for each of the case, so each of the sample that we draw that of size K on a subpopulation, there's always an irreducible error. But that's perfectly fine. Okay, but given the test that we tend to minimize this error to the extent possible, so that we can produce a consistent estimate of y. But if, let's say, it's a really big if for each of the random sample that we draw from the data, the composition of those things are different. Because due to some strange, say, data distribution, suppose that the data that and nowadays, people have been talking about, say, political polarity. Because, say, oftentimes, like from your business study, we assume that 50% of people usually they do not have those extreme political views. Right? So it's simply follow uniform distribution. Right? So for example, in random sample or in a weighted sample, if you randomly draw, say, 1,000 sample from this population. So we should assume that, all right, so the sample that we draw, they should follow the same uniform distribution, like the underlying population. But nowadays, some theorists say, no, because the politics, many countries, for example, like the French election, which is almost a week ago, it took place a week ago, said the population is highly polarized, so that people's political view should probably reflect this. I'm not sure whether it's a faithful representation of that. So if you draw 50% of your sample around this space, you probably only, so is it probably only a minor proportion of the underlying population would actually be selected. In terms of the distribution of the political view. So suppose this is the real distribution of state of the politics, in which people's political view are somehow distributed to extreme end. Then the symbol we draw is probably not very representative of the state of the politics at that moment. So what can we do? There are several obvious. Some people say, no, I don't really care about the distribution of the sample. Say, well, people's behavior can be predicted. So the first approach is probably something taken by companies like Microsoft, Amazon. say, well, I have lots of customer database, right? And for people who often shop at Amazon, they're definitely a different bunch of people than people who shop elsewhere. And you will say, and some say critic will say, no, those people who shop at Amazon, they're probably city-dwelling people with the median income above some level. They are not really representative of underlying, say, American population. But there's statisticians, their scientists, and I don't really care because I have lots of customer data, their purchasing record, their personal background information, their preferences, some of the so even some personal attributes they are inconvenient to tell you. Then say so long as I have those variables, I can predict the preference of the KD at a level. Also, for this type of approach, you say, okay, so I'll simply follow the approach to include more variable in my model. But it's not efficient. Right? Remember the blue estimated best, the white estimated, right? So the best model is the one that uses as few variables as possible to explain lots of variables. So it may not be efficient. It includes 10,000 variables just to include this smaller amount of additional variance in this plan. Probably not efficient. Okay, so just skip it. So we'll simply collect more data, but the collection effort can be costly. Say, well, like those public opinion survey, I include 1,000 simple that's not enough. Why don't I include 10,000? Then your supervisor will tell you, oh, where did you get the money to do that? Or you simply exploit more information from existing number of observation, from existing the variable that we currently had, and also the existing number of observation. Okay? That demonstrates this, right? In the tree-based model, right? Random forest, which will simply set a particular amount, a given amount of variable, right? And then we to table file, and then we simply and so for each tree that we train, we simply select some of the variable which we use as a feature for prediction. And each of the tree that decorrelate one another, so that we actually maximize the amount of variance across the number of variables that include each model. Also across the number of observations, because for each tree we use, so we simply select, we say maybe like 1/5 or even 1/10 of the population, and they are randomly drawn from the population. So this part is rendered, right? So that they should be by assumption or theoretically uncorrelated with each other. Also, the number of features that we use to explain the variation in the subpopulation also randomly chosen from the number of variables that we set for the set as the feature in the model. So maybe for each crop, there are only randomly select 3 out of 5. That's the feature for the model, right? And then the second tree with different set of 3 features out of the 5 features that were set for the model, so that they fully exploit what we already have, say the number of observation, also the number of features, and the process of downloading. And there are a couple of ways to do this, but because for now, we're going to focus around how to fix the standard error. using the last method. So we can already consider this when we say that, okay, so there's actually no consensus because here's just simulation which we simply we are assuming that, okay, so we don't know the underlying distribution of the data, and the relationship between x and y may be governed by some polynomial distribution, right? So from 1 to 10. So I simply so the process begins by first randomly select a subset of the population and then feed a polynomial regression that takes at certain degree polynomial. And then we would do 10 different round of model. We think that the model actually do not agree with each other. Right? There's no consensus model. So one of the methods that's being recommended by statisticians since the late 1970s is the resampling. So there was another assumption that if we would be able to resample, keep drawing the sample from the population many times, then the underlying the sample that we get should be close to, as we only draw one sample of the very large size on underlying distribution. And if the number of draws is large enough, then as it close to infinity, then we should get a sample whose distribution should be highly similar to the underlying population. But I mean, like, there's a 21st century, it's already like 2022, and computer science is cheap. But for each resampling duration that it might take, something like a couple seconds, nearly a second, right? It's really short. You'll probably think that, oh, that's easy. I can do that on my laptop. But when this idea was first proposed back in 1970, people think that that's not going to happen. Right? It took maybe months to draw a random sample from our population, especially in a country like US or China, which has a really large population. And the computer at that time has a huge terminal. They said, oh, you're asking me to draw 1,000 random samples from the underlying population in lieu of simply draw one random sample of size 1,000. Try to think about this. Really live in a say a medium-sized country, maybe had 100 million population. And you try to do a popular opinion survey. Okay? So you simply run the random sample, 1,000. Right. And it's already time consuming back in the 1970s. Now people ask you that, oh, you should draw one, so you should draw a random sample of size, say, 1,000 plus 1,000 times. And then we simply take the average of that 1,000 observation, randomly draw each time. Take the average of it to be average of it as the representative sample for one of this 1,000 draw. And then finally, since we have 1,000 average simple estimate. And then we take the average of that 1,000 simple estimate as our final model error, which would be your MSE squared. That sounds really phenomenal and time consuming back in 1970, but now with computer by associate, and you can easily do this on your computer. Right? So that's why we recommend this for the late 1970. So the proposed method is simply it's like drawing a symbol. It's like drawing the random symbol, but it doesn't have a population. So that should be equivalent to draw a very representative random sample of size of this map. But the one advantage of this is that because through, say, 1,000 random sampling, now you can actually get the distribution of the sample, right? Because as compared to you only draw one random sample of this size, and then use that to compute the MSE. But here we can actually get the distribution of the MSE across 1,000 data points. As compared to you only draw one random sample and estimate one MSE. Let me visualize this for you. So in traditional methods, you simply draw the random sample of size 1 draw. Use the size. Yes. So this would be your sample that you draw, and then you compete. This is simply compute the model MSE. So suppose this is okay with you, but you're not sure whether you actually fit the data. Suppose the data somehow look like this. But if you were be able to draw 1,000 random samples, each of size 1,000. So we have 1,000 draw, each size 1,000. And then we compute test MSE for each and one. So now we have C's all really close. Okay. The only different thing is that we can get a distribution all of this 1,000 over the draw. So that we can actually sort of probe the contour of the underlying data distribution compared to when we only do one draw on the data. It's sort of like those games that where they usually have a celebrity to come out of a TV show and ask him to put his or her hand into a box. If you're only allowed to touch that specific item once, then you probably don't know what it is. But if you were allowed to say simply fumbling the contour of the box and probably get the full touch, then you probably know what it is. Right? It's just like this recently. Definitely the term itself speaks, per se, the word of resimple actually speak for itself. You say resimple, meaning that you are able to simple many times, right? So you will get a distribution of this sampling as a data point. So you know, so you can probably approximate the contour of underlying population. So for this lecture, we're going to introduce you 3 different methods. So the first is your big one now, cross-metadata. And the k-fold cross-validation finally we conclude with booster. So what is lib1L, LOCV? So lib1L is just like the trend test split that you might be familiar with. So for each random draw, or say for each split, you simply use the term that you already be familiar with. So suppose you're working on data of size n. So we have data size n. So if you're using lib1L cross-validation, that's equivalent to you do trend test split n times. And for each time, you would use one observation, just one, as your testing data, using the rest of the n minus 1 as your training data, and the rest is just the same. So you fit a model on the n minus 1 as training data, use the trend model to make prediction for this single observation that's being left out. So lib1L. And then you do the trend test split and prediction test n time. That means you will make n prediction. And since you have testing, training and testing data, you have n mean squared error estimate, right? And then you take the average of that as your model MSE. So the resulting test MSE is just the average out of this n MSE. So you're sort of like you're doing the trend test split and model prediction and validation n times. But the fun thing is that you're leveraging the distribution of information from n minus 1 data point as your training data, and only make prediction for just one data point. So they have those good in common. So the good thing is that you use the information from all observations except for this one. But still, since you're going to do this in time, right? For all one observation, use each and every one of them as your testing data. And so essentially, you use all the information from all the data, and also you also average across all n quantities. So that supposedly, since you kind of average all the information from the given data, your prediction should be really precise. Okay, let's just visualize this for you. So just the simplest case. Suppose we have a observation. Right? Of course, I would say usually you won't be working on data this small. A observation for each time. Lib1, so simply lib out one observation as your testing data. Using the n minus 8 minus 1, using the other 7 observation as your training data. Right. So that's the first one. Right. And for second round, use the second observation as your training data, leaving the rest as your testing data. So that's the same for the A's. So that's our lib1L process. So that you have down then trend test split. Right? Essentially dividing the data into the training part and testing part. Okay. So now so now you can work on this to do so you simply train your model on this 7 observation, right? And then use the train model to make prediction on just one single observation. and you do this n time, right? So you have n predicted value and n test MSE. And you simply average across this to get the model MSE for the entire data. Right, so any question here before we go to talk about? Right, so for implementing this, we need to download food package, our sample, and our different NDS housing data. We need a library, our textbook, our package for our textbook. All the library, so we first need to code the data. So here you can see that we use slightly different true test split because you have asked always said require that we use the create data partition every time. I don't like the carrot package. Of course, there are other building true test split packages that you can use that we will demonstrate other than that. But essentially they are the same. But of course, so even if we use the same MSE, because they use different test split methods, so actually you think that the sequence in terms of index may be different. So you might get a slightly different result. But I think for all your assignment, actually, so long as your product, your sequence of your processing logic are correct, or something grand goes great for you. Okay, so there are different methods to do things in R. Okay, so you notice that we use GLN. You say, oh, are we supposed to work on the continuous data, but you're using GLN? I feel a little bit uneasy. Well, as I said, GLN is essentially like LN, right? So if you do not specify the link function, the GLN will just return what you would get from LN in your regression. So it's okay to still use GLN. I just want to use it to remind you what's happening. So now, for the one now observation, you just use the CVGON, which you will see that how it works differently if you specify other arguments. But here, if you do not specify any other argument, then you will just do a function call, like leave one out, cross validation. So here, the first argument should be your data, and then the second argument will be the model output. Then you will return a CVGON object. So it's essential that you should look at what's inside the CVGON object. So with the structure argument, give it a glimpse of what's inside. You see that there are 4 elements. So the first one is just function code. The second one is the size of the data, number of observations. If you uncertain this, you can simply type, I mentioned, the n row, which will return the length of the row for your data. And the third one is the most important thing. It says delta. That sounds weird. It's just the cross-validation estimate for your prediction error, for each prediction. Right? You will be doing n prediction. And that will give you n test MSE. So exactly the first number that we're bringing here, because the first number is equivalent to the result that you will get if you only do one random sample on the model. And doing this trend test split once, you get the testing MSE once. So you can check this by typing, right? You should be familiar with this, RSA Lasso model. It's the same procedure that you should get the first estimate. What about the last of the C is actually the random C that we use in our original function call. Right, so that's only for one row. So suppose that, okay, so one to automate this process. Say, for example, want to use this continuous trend test split with leave one out information to validate if a certain variable is significant or insignificant at a certain degree following the result. What can we do? Well, we can actually we should first begin by writing the function. So here I put the function code and I write a function. So I said bring the c inside that as the first argument. The second argument is just specify a univariate polynomial regression using GON, right? Without specifying even the function. But the same data is training, right? So the element that will be repeatedly executed is the degree polynomial. So here it's only specified as x. So the parameter inside the function is the element that will be repeatedly executed inside the function command. Say you want to execute a certain function 1 to 100 times, then you should, and then x will be 1 to 100. And so for each round, we will get a model of GON output, and then we put the GON output inside the CP-GON function that you see previously, right? And the first argument, of course, your data is the same as this one. The second argument is the output that you want to evaluate this. And then for each element inside it, we want to retrieve the first one, which is the first cross-validation prediction error for that round. Okay. So now we have a function, so we can test. So what would be is the change is in terms of its effect across 1 to 10 degree polynomial of ground leading area as a predictor for log price. So here I used a little trick. I used the PUR package using the map DBL function to map this function for each of the elements that's specified in the first argument. So I'm testing the polynomial degree of ground leading area from 1 to 10. So I simply map 1 to 10 to this function. So this function will automatically execute this function command of looking looking through this function code from 1 to 10. So the only thing varies is this part. So you should return 10 element vector. So you see here. So how to interpret this? So there's a sharp drop in terms of test MSE at a second degree polynomial, but after that decrease, the decrease in MSE is only minimal. So we should probably stop at second degree. That's what we can read on. But however, at around like the 8th degree, we see that actually the MSE will increase. But of course, things will be hard to explain at 30 degree polynomial. So in most circumstances, we say for this analysis, let's suggest that the ground leading area is we should probably approximate its relationship with the log price as second degree polynomial. That's perfectly normal because, for example, let's simply ask a really uneducated question. So how will you compute the degree? How will you compute the area of something like the square foot? You simply square it, right? So the ground leading areas must be like lengths of width. Or simply just square the foundation. So perfectly normal that it's only significant with the underlying, let's say the sale price, the second degree polynomial, that is simply calculating the area by the square or something, right? So that is very intuitive. So now we have done this, we're going back to k-fold cross-validation. So I will finish this in the next slide after that in this break. So k-fold cross-validation is almost exactly the same like label and out cross-validation. It's just a more general, you should interpret it as a more generalized version of they want to cross validation. Because we found the same random sampling per curve. Now we first randomly divide the data into K group instead of N group, meaning that you only do trend test split K times. Right? The K could be just the same as N. So you have a data that have contain 1,000 observations. You said I want to do 1,000-fold cross validation, and people will tell you, well, then you should go back to live one out cross validation. Or you say, oh, I want to economize time, I want to save time, we'll just do 5-fold cross validation, then you will only do trend test split 5 times. Right? That's equivalent to this just dividing it into K group of identical size and then estimate the same model K times. As compared to live one out cross validation, where we have to do that N times. Right? With the times of trend test split and estimation equivalent to the size of the data. So for each time, it's just the same. Observation within the first flow are treated as the validation set. And then the statistical model is fit on the remaining K minus 1 data. They will be used as training set. And then we can calculate mean square error for each of the K subgroup. And then we take the average of this K mean square error, which is just divide by K, right? To get a test in the model MSE. Right. That's a question here. So we just visualize this. It's sort of similar like the big one out cross validation. So suppose we have the data, right? So we randomly cut it into KPs. We use the first 1 over K proportion of data as our validation set, or AKA our testing set. The test set. Right. So for the second split, right, we use another 1 over K proportion of data as a testing set. We're using the rest as our training set. So we go on and on until we do this K test. So that so for each K segment of the data, we have our training set and testing set, right? So we will have K predicted outcome, right? And also K test and estimate. And then we average this, get our model and estimate. We just follow the same procedure as the one-hour cross validation. And empirical research have shown that, okay, so using up to 5 to 10 degree cross validation should be sufficient. So if you Google this online, you see that most replication code that people post on web or on their personal page, they usually specify CD equal 10. You say that is that the rule of that? No, it's no rule. It's just by convention using that 10 for cross validation. Dividing your data in 10 part and then do this trend test split estimation, averaging out 10 times, should be enough to get a relatively accurate test error. And of course, you can definitely do more, say 20-fold, 1,000-fold trend test split. But of course, that carries some burden because one of the biggest advantage of K-fold cross validation as compared to live one out is that simple less. We sample less. Only K time as compared to N time, which have to iterate through all the observations of the data. So you should be much faster, especially if you're working on working on large chunk of data. Or if you only have small data, then you can definitely do live one out, estimate each time. Right? And another advantage that it can be implemented was basically send algorithms. Because here we were still using CDGO and just the send algorithms. We just include one additional argument, K equals some photo that you want to understand. It can be implemented with the same algorithm as the LLCD. Right, so we will take 10 minutes right after that. We go through the article. About the K-fold cross validation. So the method that we really need to install required is simply the same, right? So we just code of this package and do the standard preprocessing test. So the only different thing is here. K equals 10. We want to do 10-fold cross-validation. We want to do 5-fold, just specify K equal 5. 20-fold, K equal 20. Right? And then we use the same math DBL to math to ask R to implement, to execute this function. And we vary by K to execute this run from K equal 1 to 10. So we can see this. Okay. And of course, the same skill also apply to binary classifiers. So here we'll show you one example. To apply for classification problems, we use the AER data. One of the data from AER and the housing mortgage data. So we need to first convert the outcome variable 1 to 0. And convert it as factor, which you should be familiar with. There's no subset required column to use as a variable. Also, we use a subset of the cases that on the observation that do not have any missing value. And then trend test split. We run the GRN regression using logic. We'll see that there's a default setting by no E. And then define a cost function, which is just the differences between the absolute differences between the response function and our predicted value. And we put it inside CBGON and then retrieve the first estimated task in SE. So it's just the same. Almost exactly like what you would get for the did one out cross validation. Okay, so let's go to bootstrapping, one of my favorite topics. So, anyone heard of bootstrap? That either as a term for your living essential or as a statistical technique. Right, so my personal story is that because I first learned it, say in the on the English speaking context, so I didn't really have a chance to know what it's called in Chinese. And after I get back and I found out I didn't read one textbook, and found that in Chinese speaking context, this method is called self-help method. That's very intuitive because when you try to construct a glue, you need a bootstrap. So you're essentially helping yourself. I think that's how they call it. And it sounds quite weird. So now we'll get down to the formal definition of bootstrap. So it's just a name, just one of many resampling techniques in which multiple samples are drawn from a given underlying population. And the statistical interests here they are calculated for each new sample, just like what I have shown before, right? It simply draws 100 or maybe 1,000 samples of identical size, and then you get some distributional statistic from that sample, and because we draw random, you draw a number of samples, lots of samples. So that you have lots of this statistic. And if you map that on the underlying data, you should be able to see the distribution of this small sample. So their distribution should work. So given that if you have done that many times, say you draw 1,000 or 10,000 random samples from the underlying population, and the distribution of this average sample estimate should be close to the distribution of the true underlying population. That's the basis. And you can analyze those statistics. So this is often used to compute reliable standard error, variance, or even to adjust for the bias, for example, like the Jack-9 method. You may have heard of it in your cognition class. So this is just one of the techniques, just like LOC. Right? But only that you here, for for each graph, we actually draw masses. So more formally, can be referred to any method that relies on random sampling, right? Just like you would do this once, but here, do this multiple times. And also with replacement. So what does that mean? Right, so before I get into it, is that we should refer to any method that relies on random sampling with replacement without assuming underlying distribution of data. Because for a random sample, we assume that the underlying data will follow a normal distribution, uniform distribution. So that if we draw this across the range of data, then we should also get a sample that also follow normal distribution. Well, that's in the, say, that was assuming that we did in the perfect form. But in most circumstances, we don't. Because political opinion data, in which people's opinion are highly polarized, right? Then or maybe in cases in which you're forced to deal with right-skewed data or left-skewed data. So this the uniformly distribution often don't help, right? So bootstrap is actually used to deal with that in this situation without assuming underlying distribution of data. So we only learn the underlying distribution of data by through repeated resampling from the data. So that you could map the multiple resampling, map it. You would be able to draw lots of samples from the population and map their calculated statistic on the data. And we should be, and those data points should be able to reveal the true underlying distribution of the population. So that's the point. Another thing is that we rely on resampling with replacement, which means some of the data point may be represented more than once, or not at all. So we'll go to this point in 50 seconds. So follow this procedure. The distribution of the error from all n bootstrap, suppose you draw 1,000 bootstrap samples, should be equivalent to the distribution that you are getting. You are able to draw a repeated sample of size. Remember the graph that I just showed you half an hour ago. You are being able to draw a random sample 1,000 times, and each sample sees 1,000 observations. And then we compute their average MS. So we have 1, 3, thousands MS. And then we can map this onto the data. And the distribution of this passive MSD, that's the data, single data, should be close to the distribution of online data of the population. If we have done this many times, say 1,000, we'll say usually 1,000 should be done. So one of the good things that he actually doesn't put any prior assumption on online distribution of data. We rely on lots of random sampling to review the contour of the data for books. So it's equivalent to you will be able to draw lots of samples. So that often used to compute standard error for auto distribution, or when the original model error highly unreliable. For example, a system equation in which the error from one equation are related to the error of another equation. So that's not very consistent. Also, they are endogenous. So we often use bootstrapping to compute thin error in those situations. But here we're going to go back, just take a step back, deal with representation problem. Because if bootstrap is the method that will represent simply with replacement, that means some data point may be represented more than once. So, for example, especially during the election cycle, election season, you say, so if you look at this public opinion results, say, well, I'm not being surveyed, so you say, I want to work on my voice. My voice didn't count. But maybe your cousin or your mother being telephone surveyed twice or thrice to the extent that she almost exhausted. Say we should stop calling. Right? That means your cousin represents 3 times those reticent. But you, 0. Your opinion are not being represented. Well, that wasn't quite an issue, the bootstrap, because suppose we are trying to draw a bootstrap sample from the data frame of only 3 observations. So in first bootstrap sample, you see that observation 3 is represented twice, and observation 2. And in second bootstrap sample, all the observations are represented. So that's good. In third bootstrap sample, the observation 2 are represented twice. Observation 3 no. Well, that's okay because if you draw multiple samples, then chances are that those should have equal probability of being represented. And given that we have resampled many times, if some observations are at higher frequency of being represented in the substance, in this bootstrap sample, that means in the underlying data distribution, those observations they probably have higher than average frequency of being appeared in the data. Then, the resulting bootstrap, say, estimation of model standard error, actually reveal this tendency to us. Right? That means that a particular value appear more frequently than other values. That could be indication that political polarity might actually be the case. In that people who have extreme political opinion are actually more frequent than you thought it would be under a uniform distribution assumption. Because we often assume that people's political opinion is somehow clustered around the mean, right? But if we simply draw another random symbol, bootstrap symbol, we found out that people having some value, especially those extreme values, actually occur more often than under the assumption of normality. Then that probably means that if there's a lot of, say, X value that cluster around the polar extreme, and the bootstrap simply actually reveal this distribution to us if you had found lots of random draw. That's the bootstrap. So the multiple representation or no representation isn't actually a problem. It actually helps us as we have reviewed the distribution of the data. And then we use all the bootstrap data to compute the bootstrap standard error. Here, if you read those textbooks, people they usually say, oh, well, you would need a very large bootstrap symbol, probably larger than 1,000 in order to obtain relatively reliable estimate of bootstrap. Stay there, just understand. But in my own opinion, you say maybe 250 to 500 bootstrap samples would suffice in most circumstances. But of course, it depends on your sample size. We have other sample size that will require you to do more bootstrap replication. And of course, the larger the number, the better it is, the more precise it is. So in our example, we'll do a simple variance estimate from the portfolio data that we analyze. Which we would draw 100 random sample from this data, compute the variance, use the boot, or we can do CI to compute the confidence interval. I should note that the confidence interval are not estimated. They're as in bootstrap application. So we will go to our problems. To do that, we need a following package. We call boundary boot to load the data. So this is data that consists of, because it's by various data that you often encounter such data in, say, analyzing stock market trend, by various distributions. So it's a data frame that only consists of 2 variables and 100 observations. We use that as our example data, easier to do. So here I define the bivariate distribution, variance function, which is just the variance covariance y squared minus covariance between x and y. X variance, y variance minus 2 times covariance between x and y. And then we actually compute using this function. We put our data as the first argument, and then we have this iterate over y to compute. Then to do this in bootstrap setting is really easy. So before that, again, like before, we just set the random seed. And we put the data, and using the function boot, putting the data as our first argument, then the function or the object that we're trying to evaluate as a second argument. And here we're going to ask R to do 1,000 bootstrap replication. So you will show the result. And you can also compute the bootstrap confidence interval bootstrap result. You can also plot. You generally follow the distribution using blue function. So that shows well the underlying data is probably normally distributed because we had valid data through 1,000 bootstrap replication. So for more substantive analysis, so here we load using our friend ME as toxic data. So we subset the required variable, required component. Also, we subset the number of the observation that do not have these values, so complete cases. And then we log transform the sale price to L sale price as our data variable. We do trend test split. So here, the different thing is this. We must define the result function that would be put into our bootstrap estimation. So here, I want R to go through each area of the observation. So the first argument should be the data, right? The second argument is the index. And our data, the data summary from our resulting data that contain no missing value is 2197. So to execute this function, you just include your data, which will be using all the data, and we have R to execute this command from the first observation all the way up to the last observation. Okay. Then to estimate using bootstrap function, the make sure that okay, the result is not particularly being distorted by observation or by any strange thing happening in variable. You just apply the bookman and you see the data, and the function you want to evaluate it, and you can ask to do 1,000 booster application. So here you see that also. So this looks really strange. So you might ask, where is my variable name? Right. I tend to believe that that's something that's probably due to the laziness of original programming. Because in booster application, they usually don't treat out the original variable name, but you can actually identify this by yourself. So to read what's inside the data, which result of the variable that you're looking at, the result from top to bottom, say T1 star all the way to T and star, that should correspond to the interceptor. The first one is always the intercept. And all the variable that go into the model, since here we put 6 on the variable into the model, so they correspond to the T2 stars. The first variable put into the model, T3 star. The second variable put the model all the way up to T7 star. The last, the sixth variable put into the model. Okay. So the original color is the original SE that estimated from your original regression without bootstrapping. And the bias color is the amount of bias. Well, the standard error here, it should not be displayed. The standard error here is the bootstrap standard error, not the original standard. The original standard error is here. So you can compare the result with the standard error that you will get from the original model output. So you'll see the amount of adjustment here. You see that this should be equivalent to the original model error. Okay. And here is the booster standard error that you get. So you can also use the same technique to verify at what degree polynomial does the polynomial regression function best capture the relationship between x and y. So we can actually do this. Again, this is just using the same technique. We write a function to ask R to iterate from the first observation all the way up to the last observation. And we put a result to a bootstrap function. So to have R to execute 1,000 bootstrap application. So you see that. Because I compare that with the original standard error that you would get on the LM function without bootstrapping, without correcting it with bootstrap application. So that is actually at second degree polynomial, the bootstrap standard error is much smaller than the original. Even though the first degree, which is just the original term, the standard error in this original format, the bootstrap standard error is only marginally smaller than this original. So you can actually tell consequences of bootstrap here. So here it should be able to have you answer the question. Okay, so the second degree polynomial is now is a faithful characterization of the relationship between the lot area and the cell price. Because in the original function, you see that lot area is significant. By after correction, I find out that it's significant. So there's probably something wrong there that's worse than smaller in the future. So I want to close it with one last example. One of my favorite example in the past year about speculative path. So how many of you have heard about speculative impact? If you were exposed to the stock market or financial market, let's say you buy investment. So I would highly recommend that you read these articles, which is the tab, which is uploaded in our reading folder. Right, speculative impact often occur when some, say, investor, usually those investors from a hedge fund investment company, they observe a country, usually developing country, for a reason that I will reveal in the cover second. But they found that some countries have exhibit these fundamental weaknesses. So what are they? Maybe those countries have low foreign reserve to back up the exchange rate of their currency. Well, that's the root cause of the Asian financial crisis back in 1997. Okay? Some private investors observed that they found that the country like Thailand, which has experienced phenomenal growth in the last decade, ever since the early 1980s. Right, they have a heated stock market, overheated real estate market, but they do not have enough foreign reserve to back up their currency. It means that if your country is living under fixed exchange rate, your stock market, your currency is backed by a fixed exchange rate, and you do not have enough anchor money, aka the US dollar, to back up your committed exchange rate. Well, if people keep, say, moving money away from your country, that means those assets that denominated in your home currency is going to right. So that's usually the beginning of the speculative attack. So the sequence of the attack usually begins with some investor observing that a country has a weak fundamental. Or maybe the country just have a really corrupted government, or the politics is really unstable. And then they begin the attack. But of course, the attack usually carry the losses, because the government can defend the attack, not with missiles or ammunition. Or you can say foreign exchange is foreign reserves ammunition. So if the government have enough foreign reserve, then they can withstand the attack by holding their prices, and then those speculators, they will suffer heavy losses. They would think that the further attack would be not worse than they would just withdraw. So upon witnessing the market's action, say attack, then the government must decide whether to defend with foreign currency they have, or withdraw, or simply devalue, to simply let your currency flow, let it flow. So the government's decision, so we'll say, the government, the market's decision, depending on the fundamental of the host government's condition. You can say it's politics, is the governability, or its current trend, whether the government is divisive, and is the level of foreign reserve and other economic fundamentals. So economic growth. However, the government's response function also depends upon the market's action. It can be that, okay, so maybe the investor that launching the attack, they did not have enough capital. So that means I should probably have way more than enough foreign reserve to withstand the attack. So what I was going to increase my determination to defend my exchange rate. Okay, so they are mutually dependent. So does that remind you of something that you have learned from your class? So that's not how we like extensive form again, what we like a game tree, right? In which the market is the first mover, the government is the second mover. So the market's decision to attack It depends on some of the fundamental condition the government has, while the government's decision to defend depends on observing the attack. Right? Well, if there's no attack, then the government do not need to proceed to this part. Right? Again, we're just terminating. The government, if the market decides to attack, then the government will need to decide whether to defend its currency or, oh yeah, this is right? Or to devalue. So let's change this to devalue. Okay, so the David White's original paper is simply just specify a two-stage program model for this matrix. And that was phenomenal at that time, back in the early 2000s. But again, people quickly witnesses that's not fundamental weaknesses. Well, what are the fundamental weaknesses? Not in the level of foreign research that this author has, but actually in the statistical model. So what seems to be the problem here? Go back to the first couple pages of this week's slide. You should be able to answer the question. Let's say the government's response function is only estimated on some part of the data, conditional on the data has proceeded to this part. Right? So, if you assume that all the information is being treated as the full data, and the government's response function, so in the original paper, is indicated it specified a program model for the market. And then the second program model followed on the same data, estimated on the same data. But it's not the case because the government only made decision upon observing the attack. But for the rest of the data, was just like wars or military-like conflict. People usually live in peace. So most of the time, people are at peace. Attack only occur some of the time. So the government response function is only estimated on some part of the data. Right? Also, the estimated standard error from the government's response function, which we use as equivalent, is correlated with the market's decision. That means, okay, so first of all, the data is only estimated on some part of the data. So the estimation result isn't consistent across all the systems. It's just like the bias variance trade-off, right? Or simply the type of problem that we will encounter in, say, the trend test split. If we only treat, say, some part of the data through trend test split as our training set, and the model we train and the result that we get out of the training is highly reliant on the sample that we obtain as a training set on trend test split. And if we do another trend test split using some random sample, we will get an entirely different result. Okay? So that's one problem there. Because the government's response function is only estimated on some part of the data. The second one is about the reliability, the consistency of the standard error. It's not consistent. Because first, you build only some subset of the data. Second, the standard error is also contingent on the market's response. Right? So that wasn't saying that this sequential approach is not a good idea or it's entirely wrong. I'm only saying that to say that there's we can improve the estimation if you really want to work through the estimation approach, and you using the existing statistical framework as suggested by the point the original output. Then there's something we can do, that is to better specify the model and also use bootstrap scenario to get a simulated scenario for this contingent choice problem. So the best example that I want to show you is actually the supplementary material, because it took lots of time to run, so I will leave that as your thumb exercise for you. So to do that, we need a get packet to get the bonus data. So you might want to check out what's inside the data. So I think you'll be running hard to understand what's inside the data if you have a look at this paper. So I would recommend that maybe in summertime you can take time to look at his paper, to read his paper, to see what was variable and how he code those outcomes. So before you do all the coding and analysis, it's definitely imperative to look at the distribution of the outcome. And so we use table to show the frequency distribution. And as you will see, speculative data is something like a rare phenomenon. So you have like very big. So before that, we need to code our data. So we need to get rid of this missing value and then recode the value. So for any observation in this variable that is originally coded as null data, we just code it as if they are originally coded as not null tag, that gives the users the explanation sign. That means the tag, so we code it as 1. And so from all those 0, they're simply coded as tag. No, that's not that. So here is the Marcus decision. But again, we need to, so for those values that have been coded as 1, it should be mapped onto the government's response function, the government's decision. So if you check out here, the tab versus non-tab. Okay. So here we already coded the attack, meaning that it's the subset of the data that will perceive this one. Right? And then among this observation, we need to code the government's action. It will be either, I actually have it in the side here, it's a non-defective. Okay, so there's nothing else I need to check. So it should be either not defective or defective. Meaning that the government actually take action to use foreign currency to back up their exchange rate. So we need to recode those values among this part of the data. So after that, we should check out the frequency distribution. And then based on the original paper, you should include a set of variable to calculate the market's expected utility, and also as a variable to approximate the government's expected utility by defending its exchange rate. And the estimation is just very easy. So first, the government's response function. The government response function is only estimated on this particular subset of the data. Okay. And here I use the logistic regression. But here we encounter another problem. So that the market decision, because in order to derive the equilibrium, if you just the equilibrium outcome, as you can say, is the original decision. Through a technique called backward reduction, we must work backward, right? So now we have calculated the government's utility when defending upon observing the market's action. So what would be the market's action? The market will also read the government's utility based on its calculation that the government will defend or not defend. Right? So you need to put this P over 1 minus P into it. Right? So to write this down formally, market's decision so you will only attack if it's expected utility from the government's two action, that the probability that your government will defend plus to multiply by all the variables that capture this utility, the market's utility. Plus the utility, the value is just a complementary utility, 1 minus the probability of the government defend. The utility that the government would not defend is simply the value. So if the expected utility conditional on the government's two action is larger than its expected utility of no attack, then the market will launch the attack. But they should also see that each of these carries some within the United States right inside. And that within error is also need to be multiplied with the government's probability of defend or not defend. So you have to see the probability. Their errors are now correlated. So that using the traditional curvature logic model is sufficient to take this into account. And then the result of these 10 errors will be consistent. Right? So now we get down to this thing. We have this. So in order to make this data to represent this, okay? So suppose the market's utility can be represented by the 7th variable, right? Here, here, here. That means we need to compile 2 7 variables and multiply them by the predicted probability of the government's action, right? And then we merge them into one. And essentially, we have the same variable, just being multiplied by the government's probability. So you can use like C bond, right? Line column. And you get it. So that's what I'm doing here. So the first sub-data is defend, and the second data is going not defend. Oh yeah, I forgot to mention this. The predicted probability, you should recall your logic function, how to make the predicted probability. Just fit the value. We combine these two sub-data into one big data as the data set which we will be used to estimate the market's action. Then we replace the output variable with then the tag. Use as our default variable. And now we have everything we need, right? We can now compute the market's response function. How to attack and how to attack. So now we have a located output. And then because the standard error isn't consistent, so we would use bootstrap standard error as in view of the estimated standard. So we just run the function, it's just the same as you previously. Put the data as our first argument is indexing to go through all the observation. And then we put this into the boot function, so that's the market data that we get from the market's response. Right? We need to calculate this estimated error. Because this estimated error is conditional on the government's too. And then the function, and do 1,000 bootstrap application. So that should print out this bootstrap standard error. And then you can compare that with the standard error that you would get if you simply run this using the GOA located function. Okay. Question? Okay, so you can play around with the code if you have time. So if we add more nuance to I would say it's a very innovative approach. So you can also extend that to work on other application of your preference. So like another like data theory setting where we want to estimate this function approaches. So any questions so far? I mean the sampling approach introduced this one. Okay, so let's code it in.